Okay, and this would be our second review session for 240 compression. It's December 3rd, 2018, and we'll kind of continue in this review from where we were last week. Now, if anybody looked at our Zoom session last week, you would have seen that Angela Student and Audra attended that Zoom session live, and we went over Unit 1, practice with input-output functions. And we went over that in quite some detail. So I'm not even going to go over that in this particular review session. If you are having any difficulty with those input-output functions, you know the kind of questions where I ask, a hearing aid provides 120 dB SPL output with 70 input. What's the gain? And then people say 50. Okay, fine. Now, same hearing aid, knee point at 40, compression ratio 2:1, blah, 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 blah. And then I always say, draw input-output function, hint, because that will help. You know those questions that you had on the midterms that you had problems with? Okay. Last week's Zoom session, go to that Zoom session, and you will see where we went over in exquisite detail going over that particular section, okay? And that's why I'm really not going to go too far in that direction at all this week. The midterm exam will be the usual, I should say the final will be the usual format. True, falses, multiple choices, fill in the blanks along with labeling some diagrams. So nothing's really changed that way, okay? Everything's quite the same, okay? What's going to be different, of course, is the content. Most of the content will be after the midterm. So most of the content will be on digital features. Digital features, like what makes digital from analog. In other words, if I pull up and share screen here, let's look at it. Share screen. Okay, see this little file folder that's open here? Linear versus compression, really don't need to go over that. You know that. Practice with input-output functions, that's what I was telling you we went over last week, okay? Output limiting versus WDRC, you should have a handle on that. That's Unit 2, that's from before the midterm. I'll tell you what you need to know from that. Have certain salient points down from that particular section, okay? So when you're looking at output limiting versus WDRC, notice the differences. High knee point, high ratio, low knee point, low ratio. For whom is this intended on the left? Severe hearing loss. For whom is this intended on the right? Mild to moderate loss. And where is the compression taking place here? For loud inputs. Where is compression taking place here? For medium and loud inputs. So this hearing aid is doing linear gain most of the time and compression less. This one's doing linear very little amount of the time, and it's almost always in compression. So the focus here is on amplifying the soft sounds, and the focus on the left is limiting the loud sounds. Here the focus is on the floor, and here the focus is on the ceiling. Okay? Seen as frequency responses when you're looking here, input-output functions. When you're looking here, same thing, but in terms of frequency responses. Output limiting would be saying, give lots of gain for soft inputs, lots of gain for average inputs, lots of gain for soft inputs, lots of gain for average inputs, and then suddenly slam on the brakes for loud inputs. Then suddenly slam on the brakes for loud inputs. On the right, you've got most gain for soft, less gain for average, less gain for loud, and that would be seen here. Most gain for soft, less gain for average, less gain for loud. Okay, WDRC on the right, output limiting on the left, WDRC on the right, output limiting on the left. Output limiting, you're mainly adjusting the maximum power output. WDRC, you're mostly changing the gain for soft inputs. Please remember, and remember well, the leftmost diagonal 45-degree angle line on input-output functions always means more gain. And the right always means less gain. Okay, essentially that. Let's leave that guy alone. We'll close it. We'll open up the next one here. Summary. This is all prior to your midterm, so I won't spend much time on this at all. Okay, looking here, a classical clinical spectrum of compression. This is a very useful picture to look at as well, describing the differences. Inputs are on the left, the arrows are the gain, outputs are on the right. Linear, lots of gain for soft. Lots of gain, whatever. The same gain for soft and average inputs would be the same gain for loud inputs, but because of peak clipping, they've stopped it. Output limiting, a close cousin of linear, same thing. Same gain for soft, same gain for average, but suddenly slamming on the brakes without the use of peak clipping. WDRC, the same kind of amplification for soft sounds, but note progressively less and progressively less amplification. As the inputs go up, the gain goes slowly down. Applying these things, WDRC for mild to moderate losses, output limiting for more severe losses. OLC versus WDRC, once again shown here. Once again, same thing shown here. Now, bill and till no longer are of any use. History, okay? We looked at bill and till as two original types of WDRC. One was WDRC confined to the low frequencies. Hi, Sam. We got a visitor here. Hallelujah. Well, very good. No worries, I see your mic is off. No worries, but I invite you, Sam, if you have any questions, to butt in and go ahead and ask, okay? So if there are any questions that you have, I'll stop sharing for a sec. Oh, we got Cole Atkinson here too. Okay, great. If anybody has any questions regarding the review for compression today, we did a review last week, and it was mostly on input-output functions. You know, the questions that people had trouble with on the midterm. So we did a detailed review on that area last week. So I encourage anybody to look at that particular Zoom session for that. What I want to concentrate mostly on in this final review is the stuff that took place after the midterm, all the digital stuff. So I was just kind of wrapping up a little bit about what we had covered prior to the midterm and was quickly getting rid of bill and till, getting that stuff out of the way. And then we would launch into what we mostly are concentrating on now. So I'll just, if you have any questions though that pop up to your head, things that you want me to specifically clarify, by all means, just yell into your mic and tell me to stop, okay? Sounds like a plan. Okay.
Yep. You answered a lot of the questions on the last session. I was able to watch that, and that really kind of clarified me a little bit, because I struggled.
Good. Okay, great.
I really appreciate that.
Okay, fantastic. Bill is just WDRC confined to the low frequencies. Till is just WDRC confined to the highs. I mean, look at these two, and then just look at, this is straight WDRC by itself. This is just WDRC happening just in the bass, and WDRC just happening in the treble. We don't think about these terms anymore. This was the old K-amp from 20 years ago, and this was the old Oticon, high-end Oticon digital hearing aids from 20 years ago. So forget that. We don't really look at that anymore. But let's do look at some of, you do have multi-channel today, and this is a two-channel hearing aid. Now the hearing aids have 10 to 20 channels at least. So this is programmability, and analog hearing aids began giving programmable, and they actually started doing programmable before they did multi-channel. And in 1995, 1996 was the end of the analog era, and the high-end analog hearing aids were both programmable and multi-channel. So you had different programs for different listening situations, and we still do that, of course, today in today's digital hearing aids. A program for listening in quiet, a program for listening in noise, one for listening to music, what have you. That hasn't changed. But that began in the good old analog era. So I can even close this guy here, and we'll go to this unit here, and there's 5 particular, maybe 3 or 4, I don't know, let's look at these things. Types of dynamic compression characteristics. There's a few questions on your final regarding this. This is the last unit we did before the midterm. And dynamic aspects just refers to how a hearing aid reacts and how fast a hearing aid goes into compression, attack time, and how fast a hearing aid releases from compression, release times. And there was various ways of doing that. This shows 3 ways. Peak detection meant a quick attack time and a slower release time, and those attack release times were fixed and always the same. When you had adaptive compression, that meant you still had a fixed attack time, but your release times would vary. You'd have a quick release time if you had like a door slam, you know, like something that was quick to become loud and quick to become soft again. But if something took a long time to become softer, then you'd have a longer release time. Then you had average detection, and that was one step better. That was variable attack times and variable release times. So if it was a door slam, you'd have a quick attack, quick release. And if the sound took a longer time to become louder and quieter, you'd have a longer attack, longer release. The reason or the advantage of this is less compression artifact, less compression pumping perception that would be audible to the listener. Then you had syllabic compression and automatic volume control. Syllabic compression was pushed by Oticon, and it simply meant fast attack, fast release times. And automatic volume control was pushed by Widex. It meant you had long attack, long release times. This one was done, AVC, to imitate the length of time it took for a user to raise his hand to change his volume control, and the length of time it took for someone to react. That was done by Widex. Syllabic detection was used along with Bill. Have quick attack, quick releases, so that you can stamp out, or you could use compression for loud, low-frequency sounds quickly to stop the bull in the china shop, to reduce the upward spread of masking, and to do it quickly. Okay, so syllabic compression was used with Bill by Oticon. AVC was used by Widex, and it was directly the opposite, and no one went to jail because no one was right or wrong. It's just the jury is out. Today's digital hearing aids use a default. They use syllabic compression for the low frequencies, and they tend to use average detection for the high frequencies. So put a star by that, because that's in your notes as well. I'll close this, and we'll look now to after the midterm. So this is the stuff we want to bear down on. So let's look at digital hearing aids and make sure we can contrast this. So here we go. Let's pull this guy up here. All right. You've seen this slide before. Digital hearing aids, remember the year they came out, 1997. The first digital hearing aid was the Widex Senso. It had 3 channels. The very next one was the Oticon Digifocus, D-I-G-I-F-O-C-U-S, Digifocus. That had 7 bands and 2 channels. Basically, when you're looking at digital, as opposed to analog, you have a mic changing sound into electricity. Then the electricity is amplified, and the receiver changes the amplified electricity back into sound. So you can see how these input sound waves, acoustic, electrical, emerge as bigger electrical and then change back into acoustic by means of the receiver. Now in today's digital hearing aids, there's nothing digital about the mic, nothing digital about the receiver. Those are simply transducers, okay? What makes digital different is sound is changed into electricity. The electricity is changed into digits by the A to D converter. The digital signal processor in the middle is manipulating and doing stuff, and then the digits are changed back into electricity, and the electricity now is changed back into sound. Okay? Basically, I don't really, here's one feature of digital hearing aids. Many frequency bands or channels. Instead of 2 or 3, like the first digital had, you got like 20, 15 at least, lots. So you can raise and lower whatever you want to do. You can literally sculpt and shape the frequency response. Another feature in Unit 5 was automatic feedback reduction. As you've likely seen on a lot of your digital hearing aids in your practicums and in your labs, when you've got the feedback reduction going on, and it's usually done by phase cancellation. Usually, okay? So the peaks that cause high frequency feedback are automatically canceled out. The hearing aid detects what frequency is giving the feedback and actually produces an opposite phase signal to cancel it out. Beware of overusing automatic feedback reduction because it can really compromise the high frequency gain given by the hearing aid. There's a real a tug of war, I find, with automatic feedback reduction because it can really reduce the possible high frequency gain that can be given by the hearing aid. Now, digital hearing aids also, we looked at compression this way as a knee point here, but digital hearing aids also adjust it from this. So when you're looking at what digital hearing aids do, you're adjusting compression from both sides. So that really means you've got more than one knee point, and you're combining linear, WDRC, output limiting, all in one hearing aid. And you can raise or lower these knee points however you like. Now, remember, you and I aren't usually doing this. When we're fitting software, we are usually doing this. We're raising or lowering the channels. This is usually what we're doing when we're fine-tuning hearing aids on manufacturer hearing aid software. But what's going on underneath the veneer, inside the guts of the hearing aid, really is all kinds of this stuff in each of those channels. You are raising and lowering knee points, okay, by adjusting the gain in those channels for soft versus average versus loud inputs. All of that's changing this stuff. So most people aren't nerdy enough to go in the software and play with these. I'm not, okay? But you should know that that's what's actually going on underneath. When you're raising a left threshold knee point, when you're moving this one up, you're basically increasing the gain for soft sounds. When you're raising the rightmost knee point, you're raising the MPO. So, you know, you're doing all kinds of, you're doing combinations of what we used to do in analog hearing aids, which were either WDRC or output limiting. Well, today's digital hearing aids are using them all. Okay, you're combining it because it's all software now. In the old days, it was the particular wiring of the hearing aid that made it WDRC, or it was the wiring of the hearing aid that made it output limiting. You couldn't change that. That was the hardware. But today's digital hearing aids are software driven. So just good for us to know that. Here's another thing you should always know about today's digital hearing aids. Look at the green line. It's linear gain given again. You got linear gain for really soft inputs, and now you've got a linear gain for slightly louder than average inputs. And that is done to counteract the very common complaint of, I hear people at tables further away better than I hear the guy right across the table from me. WDRC, remember, amplifies soft sounds by a lot and louder sounds by less. So people at other tables are softer than the guy right across from you. So WDRC is going to amplify the softer inputs by the most. People complained about that. So what many of today's digital hearing aids do is they offer linear gain for slightly louder than average inputs, meaning the guy, if you're at a restaurant and it's noisy, the guy across the table from you is going to be talking a little bit louder than normal because you're competing against background noise, and now you're giving linear gain for that person. So it's done to, and Oticon does this. It's called SpeechGuard. It's in many hearing aid, it's in the software of many hearing aid manufacturers. Just FYI, wanted you to know that. By the way, that's what Adro was doing in a certain way too. But you've seen compression. Now let's look at expansion. Now expansion is trippy. Don't freak about this one, okay? Don't freak too much about the graph here, but I just want to tell you the story. Follow the picture as I move my cursor around on the screen. Here we go. WDRC would be linear gain, then a knee point, then you're in compression, right? Low knee point, low ratio of compression. So the gain here at the white dotted line is 40, 20 in, 60 out, 80 in, or I should say 40 in, 80 out. So the gain is consistently 40. Look at expansion, the steep yellow line. The ratio here isn't 2 to 1 or 1 to 1. It's 1 to 2, meaning for every dB of input, you're getting a corresponding 2 dB output increase. And you think, what does that mean? Well, I try not to figure it out. I just let the graph tell the story. So let's follow the yellow line. 0 in, 0 out. 10 in, here's 10. 10 in, 20 out. 20 in, 40 out. 30 in, 60 out. 40 in, 80 out. 60 in, 90 out. 80 in, 100 out. So what I just said there, let's look at the white stuff here. 0 in, 0 out. My gain is 0. 10 in, 20 out. My gain is 10. 20 in, 40 out. My gain is 20. 30 in, 60 out. My gain is 30. 40 in, 80 out. My gain is 40. So your greatest gain is at and only at the knee point. 50 in, 85 out. 50 in, follow my cursor, 85 out. 60 in, 90 out. 60 in, 90 out. See that? So your gain is going, you're getting more gain and then less gain. The benefit of doing this is that unlike typical WDRC, which is giving maximum gain for soft inputs, look, maximum gain for soft input. Expansion means you're getting less gain for very, very soft inputs. And the reason why people used expansion was to reduce the internal microphone noise in quiet. It addresses the typical noise complaint of WDRC because WDRC is working its hardest for soft inputs. So in dead quiet, it's amplifying the heck out of ambient room noise. And you can hear the internal mic noise of the hearing aid being amplified because the WDRC, that's where its heart and its soul is, amplifying soft sounds, trying to imitate the outer hair cells. Expansion is used for people who have good low frequency hearing because they are the ones who can hear that internal microphone amplified noise when WDRC is working its hardest in dead quiet. But because expansion provides less gain for soft inputs, just like you saw here, that internal noise is no longer there. So when you're looking at this screen here, this left graph is showing you exactly what this one is, only I cut the bottom stuff off. And on the right, I'm just plotting things in terms of gain. Instead of output on the vertical, I'm doing gain. So WDRC is giving linear gain of 40, 0 in, 40 out, 20 in, 60 out, 40 in, 80 out. So its gain is 40, 40, 40, 40, 40. And then it gives less gain during compression. Expansion, this yellow line, if I interpreted it in terms of gain, look what it's doing. Very little amplification for dead quiet, a little bit for 20. The greatest gain is at and only at the knee point of compression. So basically expansion was often called internal noise squelch. Okay, but as HIS is trained at OTC, you are looking at it in terms of input-output functions, not that you have to walk around memorizing this crap, because I don't walk around memorizing the crap. What you need to know is that unlike WDRC, which is giving straight maximum gain for soft inputs, expansion is giving maximum gain at and only at that low knee point of compression. Maximum gain at and only at this leftmost knee point. Expansion is always found at the leftmost knee point. And the benefit of expansion is the reduction of amplification for very soft inputs. And the benefit translates into less internal amplified noise becoming audible to the client. And for whom does that bell toll? You want that expansion usually used for people who have good low frequency hearing, because those are the ones who are going to hear that. Close this PowerPoint, go to the next PowerPoint and look at digital noise reduction. I treat this one by itself. So you've got various features. You got many channels, you got feedback reduction, you got expansion, and now let's look at this biggie. This is a biggie, so it has its own unit. When we are looking at digital noise reduction, they first tried using spectral subtraction, and this is why it didn't work. You'd measure the spectrum of the speech and noise together in a noisy cafeteria. Then during pauses in conversation, like between sentences, just the spectrum of the noise is measured. And then they take number one and they subtract number two from it. So the spectrum of speech and noise minus the spectrum of just the noise, theoretically this would leave you just with the spectrum of speech. The problem is that the noise spectrum is wide and it intersects with the speech spectrum, so removing the noise removes the speech. And the example could be shown here. Okay? Noise spectrum could be the yellow. Speech spectrum could be the red. Look at how they intersect with each other. So, if you take the spectrum of both the speech and the noise and subtract just the spectrum of the noise, you're going to end up with not very much. Okay? Instead of the solid yellow line, now you're sitting there with the red dotted line. So you've really cut things out, so spectral subtraction doesn't work. Then they tried phase cancellation. Now this is important, okay? You are going to realize the importance of this when you start clinic. You're going to get clients talking to you that, oh, my Bose headphones have noise reduction. My headphones work great. How come my hearing aids can't use that? You're charging me $2,500 a piece for my hearing aids, and yet I bought these headphones for $100. And when I put them on, they cut out the noise. So how come your hearing aids cost so much? And that's going to make or break a sale if you can't answer and deliver why. Phase cancellation works with the waveform. Look at the top one and then the bottom one. They're opposite phase, so they'll cancel each other out, right? That makes sense. So phase cancellation is used in noise reduction headphones. Why not in hearing aids? Because in headphones, the speech is sent directly to the eardrum from the headphone. The noise is sampled by a mic on the outside of the headphone. Digital hearing aids don't have this luxury because both the speech and the noise are picked up by the outside mic. So if you tried phase cancellation with a hearing aid, you'd cancel out both the speech and the noise. So here's the picture. Okay, here's an ugly old headphone. Noise reduction headphones don't look like this. But I just picked an ugly old picture of a circumaural headphone just to deliver the concept here. Okay, look at the top one. Noise from outside is leaking into the ear canal and mixes with the speech, the blue, that's coming straight out of the headphone. The mic is this little red dot sitting on the outside of the headphone. It's picking up the noise too. And it flips the noise upside down so that now you can cancel out the noise that's leaking in. and thus it leaves the speech alone. So that can cancel out the speech, the noise, and leaves the speech. Okay? But hearing aids, if this was a hearing aid, the mic is sitting here, and both the noise and the speech are coming into the mic. Whereas with a noise reduction headphone, the signal you want to hear is coming from the headphone. The noise is competing in from the outside. So you have a mic on the outside of the headphone, which picks up the noise, the same noise, and flips it upside down and cancels it out. You need to be able to explain this verbally, because you will get clients coming in, smartasses, usually engineers, okay, and they're going to test you. They're going to ask you that question. And if you can't answer it, you will likely lose the sale. And they may very well walk out and refer others not to go to you. They'll say, he's just a hearing aid dealer. He doesn't know what he's talking about. You need to. And I concentrate on this a lot because a lot of clients ask this. So make sure you understand this one. Promise it's going to be asked. Spectral enhancement is another sort of method used, and what it tries to do is to pick up spectral speech cues, things that are typical to speech. The fundamental frequency of a male voice, the fundamental frequency of a female voice, the harmonics, vowel formants, in other words, the resonances of your vocal tract, and deliberately enhance or amplify these cues. It's just a different approach from digital noise reduction. Instead of reducing the noise, increase the speech. Well, it doesn't always work. Why? Here's the waveform of speech. It could be my father can beat your father at checkers. Okay. In noise, the valleys between the peaks are filled with noise. What's still sticking out? The peaks. What's the loudest parts of speech? The vowels. What do people usually have in terms of hearing loss? Poor high-frequency hearing. Vowels are low frequency. People usually have better hearing for the lows than they do for the highs. So they don't have the trouble hearing the vowels. They just can't hear what the word was. Okay, dishes or fishes. Okay, kittens or mittens. Hat, cat, fat, bat, sat, bat, they all have ah. What makes them different is the high frequency consonants, and the high frequency consonants are this area, the soft stuff. The soft stuff. Follow my cursor. Soft, soft, soft. Remember, this is a waveform. Your frequency isn't even shown on here. Okay? This is just showing you the loudness. This is the waveform of speech. Time, amplitude. Remember, as opposed to spectrum. So, during noise fills up the valleys, so it covers the high-frequency consonants. All that's left emerging is the low-frequency vowels. Well, why amplify those? Why focus the rich already have it. That's the 1%. They don't need it, okay? So spectral enhancement doesn't really cut it either. Today's hearing aids use amplitude modulation. This is how it works. The amplitude of sound is measured over time. If it doesn't change much over time, the hearing aid says that's probably noise. It's not modulating much. It's not changing in intensity over time. It's probably a fan or an air conditioner, or even background party speech babble. Okay? And in any channel of a digital hearing aid that picks this up, it's going to reduce the gain. Now, if the sound coming into the mic is like this, the hearing aid's going, ooh, the amplitude's changing rapidly over time. It must be speech. Don't reduce the gain. Okay? So that's the general gist of it. So noise reduction isn't used with one-channel digital hearing aids, because if it was used and noise was coming into the microphone and it was steady in intensity over time, like this top one here, the gain would be reduced. Well, what's the difference? That's just like reducing your volume control. That's just like turning the gain down for everything. Well, that's going to reduce the gain for both noise and speech, isn't it? So today's hearing aids have many channels, and each channel uses digital noise reduction. So if each channel is using digital noise reduction, only the channels that are picking up the steady state intensity sounds, whatever channels is picking up this, okay, is going to be reduced in gain. So maybe these channels picked up steady state. These channels picked up steady state. These channels picked up steady state. The modulation wasn't happening. So they'll reduce in gain. But mark the words well, whatever noise is reduced here, the speech in those channels is also reduced. Whatever noise was in these channels, the speech in those channels is also reduced. Whatever noise was here is reduced, but also the speech in those channels. So this is better than this, okay? The best way to state it is noise reduction, the best digital noise reduction reduces or minimizes the impact on the speech. This totally ruins it because you're turning the gain down for everything. That's just like being in a noisy place and turning the volume down. Well, yeah, you're going to reduce the gain for both speech and noise. That's not going to separate speech from noise. Heck no, it ain't. So this is better than doing this because at least you're just reducing gain in smaller areas. But the point is this, you're not increasing signal to noise ratio. You're really not increasing the reception of speech. You are rather, I would put the emphasis on a different syllable, you are getting less impact. In other words, you're ruining the speech less with this than you are with this. Okay? So that's the important concept to take home about digital noise reduction. What is its main benefit? It makes you feel more comfortable in noise, but it does not, repeat, not increase the signal to noise ratio. Okay? It does not objectively increase speech understanding in background noise. Rather, the best digital noise reduction minimizes the impact on speech. That's a totally different way of putting it. So now we'll close that one and we'll go to Unit 7 and we'll pull this guy up in terms of PowerPoint. Okay, and we'll talk a little bit about directional microphones. These are the salient points to recognize about directional microphones. Here we go. Okay, you had lots of stuff about why you need to do that. We don't need to focus on that. By the way, we can talk about this slide here, speech in quiet. The red might be the low frequency vowels. The blue might be the high frequency consonants. And you've got this in time going up. My father can beat your father at checkers. If background noise comes into the picture, that's like the sea flooding the lowlands. The background noise covering the high frequency consonants. A digital hearing aid, digital noise reduction, cannot remove the water without at the same time snapping the trees. That's what I meant in the previous slide, where I said when it reduces the gain in certain channels for the noise, it's also reducing the gain for the speech. Very important to keep that in mind. So, that's this stuff we showed you here. Digital noise reduction does not at this time objectively, reliably, statistically improve speech reception and background noise. It does improve subjective listening comfort in noise, however, and that's important because if a person isn't happy wearing the hearing aids, they're going to end up in a drawer. So you want to keep the hearing aids on the person's ears. So digital noise reduction, addressing the comfort issue, is a very important thing to do. But make no mistake, it does not objectively increase speech understanding and noise. For that, you need to increase the signal to noise ratio. So if you can bring a hearing aid up to a speaker's lips, you've increased the SNR. D-mics help to do that. Remote mics help to do that, and FM systems help to do that. Here's an important slide. Make sure you know what signal-to-noise ratios are, okay? That's the level of the speech you want to hear compared to the background noise. So 70 dB speech and 60 dB noise is a plus 10 SNR. 60 speech and 60 noise is a 0 dB SNR. 60 speech and a 70 dB noise is a minus 10 SNR. Keep that, memorize that, make sure you know that, okay? Now, when you look at this slide, memorize this one too for the final. It's important. When noise is soft, around 55, people speak around 61. That's a plus 6 dB SNR. When noise is now 65, people speak around 68. That's a plus 3 SNR. That's harder. When noise increases another 10 dB to 75 dB SPL, the speech is often at 74. That's a minus 1 SNR. That's challenging. So that's, I guess, what I need people to realize is the noise may increase, and the speech does too, but the noise is increasing usually faster than the speech. So in noisy situations, the signal-to-noise ratio becomes poorer and poorer. Here's another slide you need to have committed to memory, okay? Speech and noise, if they are of similar intensity, look at the bottom one. If they are of similar intensity, you'll get about half the speech, okay? Especially if you can't see the person and read his lips. It's going to be, you'll get about half the speech. And that's if you've got normal hearing. Okay, to get about 50% of speech, you'll get that with a 0 dB signal-to-noise ratio. But if you've got a mild to moderate hearing loss, sensory neural, I don't mean conductive, sensory neural, an additional 5 is required for the person to get 50% of the speech and noise. And that's why the magic number is around 5. Directional mics constantly try to hit that number. Killian, who was a researcher who had invented the K-amp, okay, Killian had said that each additional dB that you can increase the SNR, that'll result in a 10% speech improvement. Well, I think he's exaggerating, even if you've increased it by only 5%. And directional mics, do they improve the signal-to-noise ratio by 5? Not really. D mics in real life increase the SNR by about 2.5, maybe 3. So 2.5, let's say 2 to 3. You've increased it by, let's say, 2 dB. And if each dB you've increased the signal-to-noise ratio gives you 5% and not even 10, 5 times 2 is 10%. A 10% speech improvement is pretty good. It's not bad. So the pure tone average, if you're looking at hearing losses getting worse and worse, look at what's the signal-to-noise ratios that are required to get 50% of the speech. And if directional mics can only give you a 5 decibel maximum speech improvement, you can see that directional mics are really only good for mild to moderate losses. When you start getting into severe losses, directional mics don't cut it anymore. When you start getting into severe losses, you're going to need something better. You're going to need a remote mic that usually is bundled with the hearing aid in question, or an FM system, some other assistive listening device. D mics don't cut it for past a mild to moderate loss. Here's how they generally work. What do you mean we're lost? I thought you bought a directional hearing aid. Well, they don't help tell the direction of sound. D mics always have 2 doors. Here's an omnidirectional mic, a regular mic, 1 doorway. A D mic has 2 doorways. Here's what the philosophy. If the sound hits a diaphragm, it wiggles, and that'll make the mic change the sound into electricity. But if sound hits the diaphragm equally from opposite sides, you've got cancellation. So let's watch how a D mic works. Sound comes in from the front and wiggles the diaphragm and goes on. But if you're having sound coming in from the rear, there's a filter stuck in one of the doorways, and that slows the passage of sound down. So if sound's coming from the rear, it gets slowed down so that by the time sound comes around the front, they meet at the diaphragm at the same time, and there is cancellation. That's generally how D mics work. So when you're looking at this stuff, D mics are what do you call it? They are characterized in terms of their polar plots. So the blue is an omnidirectional mic. Think of the 0 as the guy's nose, the 180 as the back of his head, the 270 and the 90 as his ears. Okay? Directional mics are equally sensitive to sounds in all directions. I should say not directional mics, omnidirectional mics, omnidirectional mics, okay? The three here, the red, the black, and the green, those are three different kinds of directional mics. Now, are directional mics more sensitive to sounds from the front? No, they're the same. Look at my cursor. Directional mics are simply less sensitive to sides and the rear. So the red one was called a cardioid directional mic. And the pinch point here is called the null. And the -30 means that right at the null, this directional mic was 30 decibels less sensitive than an omnidirectional mic. So to sounds coming straight from behind, this directional mic was 30 dB less sensitive. But a circle has 360 degrees. So although it's 30 dB here, it's only about 5 dB here, and maybe 10 dB here, okay, and maybe 20 dB here. So you got to take an average. So you're looking at the difference between the red and the blue, 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 and you're adding up those differences 360 times. You'll get a great big number, and then when you divide by 360, you get the average. And the average is called the directional index, DI, and it indicates the ratio of sensitivity to frontal sounds compared to its sensitivity to surrounding sounds. So the DI that I'm circling here is the average difference between the red and the blue, red and the blue, red and the blue, red and the blue, all the way around the circle. And the directional index is usually around 5. That's what the average ends up being. And the directional index is used to predict the signal to noise ratio improvement offered by any directional mic. Once again, the directional index is shown there to predict the signal to noise ratio improvement that will be provided by some directional mic in question. Now the black one is a supercardioid and the green one's a hypercardioid. Notice that they're even less sensitive to sounds from the sides than the cardioid, but they're more sensitive to sounds from the rear. Another thing to notice about them is they have two nulls, one here and one here. Weird, huh? Anyway, don't worry about this so much. Basically, directional indexes are used to predict the signal-to-noise ratio improvement for speech that might be provided by a specific directional microphone. Another term to know is automatic directionality versus adaptive directionality. Automatic, adaptive. Automatic just means the hearing aid shifts from omni to directional mic by itself, depending on the listening environment. It means that the listener doesn't have to change the direction out from omni to D mic. Okay, the hearing aid makes the decision by itself, depending on the listening situation. If it's a noisy situation, it'll go into D mic. If it's a quiet situation, it'll go to omni. Adaptive directionality means the polar plots will change depending on the listening situation. So you might end up going from cardioid to supercardioid to hypercardioid to God knows what, depending on the listening situation. So it gets pretty complicated, but you know, that's just the general stuff that you'll hear about. So anyway, digital noise reduction and directional microphones. Here's how to qualify them, to summarize them all together. Digital noise reduction gives subjective listening comfort to a client. Directional microphones give objective improvement in speech reception in terms of percent. And together they make a good team. One's the head, one's the heart. One's the science, one's the art. Okay? And essentially, that's the last slide of that particular one. So now, I will share screen and finish the last unit here, and that was on ADRO. Okay, so let's shut this one down, and let's go to ADRO. Adaptive Dynamic Range Optimization. Now, this is a matter of giving linear gain once again. Okay? And the focus here, we just covered this one a couple of weeks ago in this very class. It's our last unit. And it was invented in Australia. And what they tried to do was this. Look at the top waveform. See the peak to valleys in it? ADRO says this is what WDRC does. What does WDRC do? Amplifies soft sounds by a lot and loud sounds by little or nothing at all. Well, now let's draw on this PowerPoint here. Let's make sure we really have this here. So if I go to home here and I want to, whoa, I don't like that. Come on, I want to draw something here. There. You see that? That's a soft part. Okay, here's a soft part. Okay, right there, right where I'm drawing. Soft. Soft. I'll even make this thing narrower so it's really, so I can really concentrate on soft part. Soft part. Soft. Soft. Soft and soft. See that? Okay, because that's what WDRC does. It amplifies the soft sounds by the most. So if this top orange sound wave is coming into the hearing aid, WDRC is going to do this. It's going to amplify the soft sounds by the most. It's going to amplify this by the most. And then it's going to amplify the louder part. So I'm going to copy this. Ooh, copy. And then I'll hit paste. If I get another one. But it's going to amplify the louder stuff. This, it's not going to amplify it by as much, because that's what WDRC does. It amplifies soft sounds by the most and loud sounds by less. So this is the louder part. Yeah, you get a little bit of amplification, but not as much amplification as is being given here. Okay, look at from here to here versus here to here. So what's being done is you are ruining your peak to valley contrasts with WDRC. This here, your peak to valley contrasts are no longer as good. ADRO says that's what the problem is with WDRC, is it ruins the peak to valley contrasts in aided speech. And that sucks. They say what we do instead is we provide linear gain. So look, the top waveform hasn't changed from WDRC to what ADRO does. Notice that? So that's just the input sound wave. But because ADRO provides linear gain, ADRO has a much larger peak to valley contrast because it's amplifying the loud inputs and the soft inputs by the same amount. Okay, and therefore you've got a bigger peak to valley contrast and you've got crystal clear aided speech. And you might say, well, why would you do that? Because linear hearing aids suck. I mean, that's why we replaced them with compression hearing aids. They used peak clipping. Ah, says ADRO. We get around that. So what ADRO does, okay, is it uses rules. And it says for any hearing loss, if 30% of the aided sound falls below audibility, increase the linear gain. And if less than 90% is below the loudness comfort, so look at this blue pole, that's maybe someone's UCL. And this one might be someone's audibility, just barely audible. So if this much sound falls below audibility, increase the linear gain. And if there's more than 10% of the aided output that's above the person's UCLs, reduce the linear gain. So what's happening in the Adro hearing aid, here's typical WDRC on the top, low knee point, low ratio, and it's fixed. Adro does this. It'll provide most linear gain, provided that the audibility is still there. But if 90% of the aided output is no longer below the guy's UCL, it will reduce the linear gain. Remember, as you go to the right, the gain goes down, right? As you go to the left, the gain is up. And you can follow that here. I mean, let's look. 50 in, 90 out. Okay, here, 70 in is about 90 out. So you can tell that as you go to the left, this is linear gain, this is linear gain, this is less linear gain, this is more linear gain. Okay, so if the sound carries on, and once you reach a point where 30% becomes inaudible, whoomp, increase the linear gain. The linear gain stays at that increased amount until 10% of it goes beyond the person's loudness discomfort, boom, reduce the linear gain. So you're always sliding. You're using a more linear gain or less linear gain, but by gum, your gain is always linear. Okay? And that's the secret behind Adro. I can finish this off by just saying, and that's what you're doing, is you're trying to imitate. Oticon uses this approach. Remember we showed you this earlier? It's getting around the problem of WDRC2 by providing linear gain for slightly louder than average inputs to address the problem of, oh, I hear people at other tables better than I do the guy right across the table from me. Well, Adro's approach is different. They're using linear gain, but they're using more or less, according to the different rules that get violated. An audibility boundary and a comfort boundary. And these are set up, custom made for each listener. So please don't think that it's all the same in all the hearing aids. It depends on the hearing loss that's entered, of course. So anyway, here's basically the gist of things. Here, when you've got WDRC, because it muddies the speech signal, because WDRC does this, because it reduces the peak to valley contrasts, therefore it relies on the necessity of using all these different programs for listening in noise, for listening in quiet, for listening to music. But if you're using good old Adro, they're saying, because it's preserving the peak to valley contrast, because it's doing this, okay, therefore you don't have to rely as much on all these different props and these things so less needs for handheld remote controls, less complexity. Here's the final way to take this home. Adro brags about their situation like this. This is a normal dynamic range. The bottom, the top, here. Pictures talk louder than words. So look at the bottom of the slide, look at the top of the slide. Okay, call this 0 dBHL, call this 120. Okay, when you've got sensory neural loss, now you're here. Okay, so what does WDRC do? Listener can't hear the bottom half of input sound. The floor of hearing sensitivity is elevated, while the ceiling of loudness tolerance is unchanged. Look at that white up here. That's unchanged. So what does WDRC do? It lifts the bottom to fit into this. So it does this. So look at how the picture's distorted. Look at how the bottom of this chair, see the chair here, you still see the roof here, okay? Normal dynamic range, reduced dynamic range. If you amplify soft sounds by a lot and loud sounds by little or nothing at all, like WDRC does, you get this. Adro instead does this. Now, where's the bottom of the lady's chair? It's gone. See? And where's that white on the top? It's gone. What ADRO does is it concentrates not on the whole dynamic range. It's looking at the middle. And it's looking at the dynamic range of the input signal. In other words, if I go to this, I'll show you what I mean, and then we can cut our review down to a close here. Whoops. ADRO tries to look at the middle parts of the wave. See where my cursor is? Actually, maybe I can even draw again. I'll just concentrate on just explaining this. ADRO does this. Concentrates on the middle part of the wave. The middle part, see that? Okay? And it concentrates on giving linear gain to that. And if I went to here, I could have drawn that here too. Okay, ADRO focuses on doing this. Looking at the middle. Okay? Or looking here. Looking at the middle part of the input speech dynamic range. Okay? And in so doing, when you're doing that, okay, instead of, you've got this this is normal range of a listener. This is the dynamic range of the person with sensory neural loss. WDRC does this, distorting the picture. But because ADRO focuses on giving linear gain and on giving linear gain to the middle parts of the input speech, the middle part, we've done this. We've left the clarity there, the peak to valley contrasts are there, but what you've done is you've not distorted the picture. Unlike this, you got this. So again, notice that the white on the top here is not there. The bottom of the leg isn't there of that lady's chair, but the part that you're concentrating is on the middle. So ADRO is sold by Sam's Club, Hearing Lab Technology. I think it's got a new name now called Lucid. Okay? And because you all are living in the States, you should know what ADRO means. Adaptive Dynamic Range Optimization. Adaptive Dynamic Range Optimization. Know what the acronym stands for. It was invented in Australia, and it's only sold in the US at Sam's Club. Just FYI, thought I'd tell you. That's the end of this review. All right? Cole Atkinson, I wish you good luck on the exam. I'm sure you'll do just fine. Remember, if you're looking at input-output functions, last week's Zoom session really covers that. I will stop recording now and bid you adieu. Good luck on your final. He writes, thank you for the review. It cleared things up for me. Excellent. Glad to hear that. Okay, I'll stop recording now.